Good evening, ladies and gentlemen. Today, I want to go through the most important math problems of all time. This took quite a long time to make, so it would be nice if you subscribed. Anyway, as always, the links to the research are in the description. Also today, we actually put some photos for some visual aid. And without a further ado, let's begin. There is a moment sometime in the late 17th century where a man named Pierre de Fermat picks up a copy of an ancient Greek math book, reads a particular page, and decides to write something in the margin. Not a footnote, not a citation, just a small note in Latin, squeezed into whatever white space was left on the page. The note says something like, "I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." Then he closed the book and, as far as anyone can tell, never wrote the proof down. He died 9 years later, and that little scribble and that little margin would go on to haunt mathematics for 350 years. But that story doesn't start with Fermat. It starts much earlier, in the dirt, basically, with people drawing shapes. Around 2,500 years ago, Greek mathematicians had a very specific obsession. They wanted to understand the world through geometry, through shape and ratio and form, and they had two tools, a compass and a straight edge. No measuring, no numbers written down, no arithmetic in the modern sense, just a compass to draw circles and the ruler to draw lines, and from those two tools they wanted to construct the universe. They managed an extraordinary amount with those two tools. They could bisect angles, they could construct perfect squares, they could build regular polygons. They could do things that would take pages of algebra to describe, just by drawing, and the logic behind why those constructions worked was as clean and tight as anything in mathematics today. But they had three problems they couldn't crack. Three constructions that seemed like they should be possible, but every attempt fell apart. The first was squaring the circle. Given any circle, construct a square with the exact same area using only compass and ruler. The second was doubling the cube. Given a cube, construct another cube with exactly twice the volume. The third was trisecting an angle. Given any angle, divide it into exactly 3 equal parts. These are the kind of problems that look like homework. They don't sound impossible, and the Greeks worked on them for centuries. Smart people who understood geometry better than almost anyone who came after them. They couldn't do it, and they didn't know why. The reason why came 2,000 years later, and it came from a completely different branch of mathematics that the Greeks hadn't invented yet, algebra. Specifically, a field called Galois theory, named after a French mathematician named Évariste Galois, who died in a duel at the age of 20, the night after he'd finished writing down his ideas. The theory he developed showed that certain numbers just cannot be constructed with compass and ruler. Pi, the ratio of a circle's circumference to its diameter, is one of those numbers. It's transcendental, meaning it's not just irrational, it lives somewhere beyond the reach of algebraic equations altogether. So squaring the circle was never going to work. Not because nobody was clever enough, because the number itself was unreachable by the tools allowed. This is the thing about mathematics that keeps coming up over and over again. The reason a problem can be solved is often not what anyone expected. The problem looked like one thing and turned out to be something else entirely. The Greeks thought they were trying to find better geometric techniques. The actual obstacle was hiding in the structure of numbers themselves, and you'd need a whole new language to even see it. That pattern, the problem being something other than it appears, is going to come up every single time in this story. So back to Fermat. Fermat was a French lawyer who did mathematics as a hobby, not a small hobby. He was probably one of the best mathematicians alive in his time, but he had a habit that drove everyone around him absolutely insane. He would announce results and almost never write down the proofs. He claimed he had the proofs. He just didn't feel like writing them out. Historians believe most of those unwritten proofs were probably correct. He had an almost freakish intuition for number theory. The book he was reading when he wrote that fateful margin note was called Arithmetica, written by a Greek mathematician named Diophantus. The relevant page was about the Pythagorean theorem, specifically about what are now called Pythagorean triples, sets of three whole numbers where the first squared plus the second squared equals the third squared. 3, 4, 5 is the classic example. 5, 12, 13 is another. There are infinitely many. Fermat was looking at this and asked himself, what if you raised it to the third power, or the fourth, or any power higher than 2? Could you still find whole number solutions? Three whole numbers, a, b, and c, where a to the power of n plus b to the power of n equals c to the power of n for any whole number n bigger than 2? His claim, scribbled in the margin, was that you cannot. There are no whole number solutions, none. For any power greater than 2, the equation has no answers in the whole numbers. And he said he had a proof. That claim is what would become known as Fermat's last theorem. The word last doesn't mean he thought it was his greatest result. It means it was the last of his stated claims that anyone managed to verify one by one. Over the following centuries, mathematicians went through Fermat's various claims and proved them. This one held out. Leonhard Euler, the most prolific mathematician who ever lived, proved the case for n equals 3 in the 1770s. Sophie Germain, working in the early 1800s at a time when women were not allowed to attend universities or submit papers under their own names, so she submitted under the male name Monsieur Leblanc, proved the theorem for a whole class of prime numbers. She also corresponded extensively with the legendary Carl Friedrich Gauss, who only learned she was a woman after the French army, during the Napoleonic occupation of Germany, went to check on her welfare at her personal request. Gauss said the revelation had given him a higher opinion of her, which for a man like Gauss was not a small thing to say. The case for n equals 5 was handled in 1825 by two mathematicians working independently, Adrien Marie Legendre and Peter Gustave Lejeune Dirichlet. By the middle of the 19th century, Ernst Eduard Kummer had developed whole new mathematical machinery in ring theory while trying to attack the problem, and showed the theorem held for a large class of primes, though not all. By the 20th century, computing power let mathematicians verify the theorem for all exponents up to 4 million. That sounds like a lot. Against infinity, it is nothing. The proof kept resisting. Every approach bent and broke. And as the decades went on, a kind of resignation set in among professional mathematicians. The problem was widely seen as isolated. Proving it would be satisfying, but it didn't seem connected to anything deeper. It was a mathematical orphan. That changed in the 1950s in Japan when two mathematicians named Goro Shimura and Yutaka Taniyama made a remark that would eventually shake the entire field. They were thinking about two completely separate mathematical worlds. On one side, elliptic curves, which are smooth curves described by equations with a specific structure, used for centuries in problems about calculating things like the arc length of planetary orbits. On the other side, modular forms, which are these extraordinarily symmetric mathematical functions that live in the complex plane and have properties so rigid and structured that they were considered a completely different animal from elliptic curves. Shimura and Tanyama looked at these two worlds and said, maybe they're the same world. Maybe every elliptic curve can be paired up with a modular form. Maybe underneath everything, these two different mathematical objects are secretly the same kind of thing, seen from different angles. This was the Tanyama-Shimura conjecture. Most mathematicians thought it was beautiful, but probably unprovable. Tanyama himself died by suicide in 1958, at the age of 31, a few weeks before he was supposed to be married, leaving behind a note that said, among other things, he didn't know exactly why he felt such uncertainty about himself. Shimura continued, he always believed the conjecture was correct. In 1984, a German mathematician named Gerhard Frey made a stunning observation. If Fermat's last theorem were false, meaning if there actually existed some whole numbers that solved the equation for some power greater than 2, then you could take those numbers and use them to construct an elliptic curve. And that particular elliptic curve would have properties so strange, so wildly at odds with how elliptic curves behave, that it almost certainly couldn't correspond to any modular form. Which meant, if Fermat is false, the Tanyama-Shimura conjecture is false, which means the contrapositive. If Tanyama-Shimura is true, Fermat is true. Ken Ribet completed this logical chain in 1986, and when the news got out, it changed the entire game. Proving Fermat was now equivalent to proving Tanyama-Shimura, at least for a class of elliptic curves called semistable ones. And Tanyama-Shimura, while still widely thought to be impossibly hard, was at least a living mathematical conjecture connected to a dozen other things. It wasn't isolated anymore. Andrew Wiles heard about Ribet's result and made a decision he told almost nobody about. Wiles was a British mathematician at Princeton. He had first encountered Fermat's last theorem as a 10-year-old in his local library, reading a book about it, and had been captivated. As a professional, he'd moved on to elliptic curves because that was productive territory. He had a background in exactly the right kind of mathematics. And when he heard that Fermat and Tanyama-Shimura were now linked, he quietly set aside what he was working on and started, in secret, on what most people in his field considered an impossible problem. For 7 years, he told almost nobody. He didn't go to conferences. He didn't share his progress. People around him assumed he'd run out of ideas and was taking a break. He wasn't. He was working every day in his attic, completely alone, building new mathematical machinery from scratch. He used techniques from Iwasawa theory and from Kolyvagin Flach systems, and from the theory of Galois representations. He invented things that didn't exist before. In June of 1993, he announced a proof at a series of 3 lectures at Cambridge. The lectures were titled with deliberately vague names. Nobody in the audience knew what was coming. By the 3rd lecture, when he wrote the final line and said quietly, "I think I'll stop here," the room erupted. It made the front page of the New York Times. And then, 2 months later, a gap was found. The gap was in the Kolyvagin Flach part of the argument. Nick Katz had been reviewing the manuscript and found a step that didn't hold. Wiles tried for weeks to fix it. He brought in a former student, Richard Taylor, to help. For over a year, the mathematical community waited. Wiles worked. At one point, he was ready to admit that the approach might genuinely be broken. He was going to abandon that part of the proof. Then, on the 19th of September, 1994, Wiles had what he later described as the most important moment of his working life. He had gone back to look at the failed Kolyvagin Flach method to understand exactly why it failed, and in examining the failure, he suddenly saw that the failure itself could be used in a completely different way, combined with the Iwasawa theory approach he'd abandoned earlier. The 2 methods, each insufficient on its own, together worked perfectly. He described looking at it and finding it so beautiful he could barely think for 20 minutes. The corrected proof, spread across 2 papers totaling 129 pages, was published in 1995. John Conway called it the proof of the 20th century. What Wiles had done wasn't just close a 350-year-old question. He had proven the modularity theorem for semistable elliptic curves, and in doing so, he'd basically opened a door between 2 previously disconnected kingdoms of mathematics. Within years, mathematicians were walking back and forth through that door, solving problems that had been stuck for decades. The work became a cornerstone of something called the Langlands program, which is an ongoing and enormously ambitious project to find a grand unified theory connecting different areas of mathematics, something like what physicists dream about for physics. The Langlands program isn't a theorem. It's more like a very detailed and very radical guess about the deep structure of mathematics itself, and Wiles' proof became one of the first major pieces of evidence that the guess might be right. One more thing worth noting: there is still the question of whether Fermat actually had a proof. Almost certainly not. Almost certainly, the proof he claimed to have was wrong, built on some error he never noticed. The mathematics needed to actually prove the theorem didn't exist in Fermat's time. It required concepts developed 2 centuries after his death. Whatever he had in mind, it wasn't this. But for those 350 years, the impossibility of verifying or disproving his casual margin scribble kept the problem alive that turned out to unlock something much, much larger. The year 1900 was when mathematics got its own agenda for the next century, and one man decided to set it. David Hilbert was a German mathematician at the University of Göttingen and is widely considered one of the most influential mathematicians of his era. He had a particular philosophy that every mathematical problem could, in principle, be solved. He believed in the completeness and consistency of mathematics as a system. He believed you could always find an answer if you worked hard enough with the right tools. In August of 1900, Hilbert stood up at the International Congress of Mathematicians in Paris and gave a speech that would shape the direction of mathematical research for the entire 20th century. He laid out 23 problems, all unsolved at the time, all chosen because he believed they pointed toward the deepest questions in the field. His opening words were, "Who of us would not be glad to lift the veil behind which the future lies hidden?" Some of those problems were technical, some were philosophical, some have since been solved. A few have turned out to be unsolvable, not from lack of trying, but because they are genuinely, provably unanswerable within formal mathematical systems, something that Hilbert himself could never quite accept. The proof that some of his questions were unanswerable came from Kurt Gödel in 1931, when Gödel published his incompleteness theorems and showed that any consistent mathematical system powerful enough to describe arithmetic will always contain statements that are true but unprovable within that system. This was one of the most devastating intellectual shocks the field had ever absorbed. Hilbert's dream of a complete, consistent, and fully decidable mathematics was shown to be impossible in principle. But several of Hilbert's problems were solvable, and working on them drove decades of research. And one problem from his list, the eighth, is still open. In fact, it might be the most important unsolved mathematical problem alive today. He called it Prove the Riemann Hypothesis. Bernhard Riemann was a German mathematician who lived from 1826 to 1866, died of tuberculosis at just 39 years old, and in his short life produced work of such depth and originality that it reshaped mathematics and, eventually, physics. His work in differential geometry laid the groundwork for Einstein's general relativity, which is a strange kind of afterlife for a pure mathematician who had no way of knowing that was coming. In 1859, Riemann published a paper 8 pages long, just 8 pages. It's been called the most important paper in the history of number theory. In it, Riemann was trying to understand prime numbers. Prime numbers are whole numbers bigger than one that can only be divided by 1 and themselves: 2, 3, 5, 7, 11, 13. They are the atoms of arithmetic, in the sense that every whole number greater than 1 can be built by multiplying primes together, and in exactly one way. 12 equals 2 times 2 times 3. 30 equals 2 times 3 times 5. The primes are, in this sense, the building blocks of all numbers. But where do they live on the number line? Is there a pattern? Is there a formula? The ancient Greeks knew there were infinitely many primes. Euclid proved that around 300 years before the Common Era, with an argument so clean, it still works exactly the same way today. You assume there's a largest prime, multiply all known primes together, and add 1, and the resulting number is either itself prime or divisible by a prime not on your list, which is a contradiction. Knowing there are infinitely many primes is not the same as understanding how they're spaced, and as you go further out on the number line, the primes thin out, they become rarer. There are 78 3-digit primes. There are only 21 4-digit primes. As numbers get bigger, primes get less frequent, but they never stop. Carl Friedrich Gauss, who is arguably the greatest mathematician who ever lived and who was doing serious mathematics by the age of 15, noticed something in the late 1700s. The density of primes around any number n tends to be approximately 1 divided by the natural logarithm of n. This is the prime number theorem, and it tells you, roughly, how many primes you'll find in any stretch of the number line. It was proven rigorously in 1896 by two mathematicians working independently, but Gauss had seen it empirically a century earlier. Riemann went further. He asked, can we be more precise? Can we not just know the average density of primes, but understand the error, the deviation from that average? And to answer that, he introduced one of the most strange and beautiful objects in all of mathematics. He took a function that Euler had studied, called the zeta function. For any input s, the zeta function adds up the series 1 plus 1 over 2 to the power s plus 1 over 3 to the power s plus 1 over 4 to the power s, and so on forever. When s is a real number bigger than 1, this sum converges to a finite value. Euler had already noticed something profound about this. The sum, which involves all the whole numbers, can be rewritten as an infinite product involving only the prime numbers. The two calculations give the same answer. The primes and the integers are, in this sense, two faces of the same mathematical object. Riemann extended the zeta function into the complex plane, allowing s to be a complex number, meaning a number with both a real part and an imaginary part. And he found something extraordinary. The zeta function in the complex plane has infinitely many zeros, points where its value is exactly 0. Some of those zeros are trivial ones at the negative even integers, but there are infinitely many non-trivial zeros, and they all seem to have their real part equal to exactly 1/2. They all live on a single vertical line in the complex plane. Riemann conjectured that this is always the case. Every non-trivial zero of the zeta function has real part equal to exactly 1/2. That's the Riemann hypothesis. Why does this matter? Because those zeros, wherever they are, directly control the distribution of prime numbers. The prime number theorem gives you the trend, but the zeros of the zeta function determine the error around that trend. If the Riemann hypothesis is correct, those errors stay bounded. They grow at most like the square root of n. The primes are, in a precise sense, as evenly distributed as they possibly could be. If the hypothesis is wrong, and some zeros wander off the critical line, the distribution of primes becomes much more chaotic, with unpredictable, wild swings. As of today, more than 10 trillion zeros of the zeta function have been computed by machine, and every single one of them lies exactly on the critical line, not one exception. In almost any other branch of science, 10 trillion confirmations would be considered proof. In mathematics, it's evidence, not a proof, and there's an enormous difference. There could be a zero off the line at some unimaginably large value that no computer has ever reached, and one counterexample would kill the entire hypothesis. The hypothesis has been on every major list of the most important unsolved problems in mathematics. It was on Hilbert's list in 1900. It's on the Clay Mathematics Institute's Millennium Prize list from the year 2000, which means there is $1 million prize waiting for whoever proves it. It's been on the list for 166 years, and nobody has come close. What would it mean if it were proved? Several thousand mathematical papers have been written that begin with the assumption that the Riemann hypothesis is true and derive results from it. If the hypothesis were proved, all those results would become theorems overnight. The entire field of analytic number theory would get a massive structural upgrade. Cryptography, which depends on certain facts about prime numbers, would be affected. Algorithms for testing whether a number is prime would be provably efficient in ways they currently can't be confirmed to be. There is also a genuinely strange connection to physics. Researchers have noticed that the distribution of the gaps between the zeros of the Riemann zeta function looks remarkably similar to the distribution of energy levels of certain quantum mechanical systems. The Montgomery-Odlyzko law, observed in the 1970s, shows that the zeros of the zeta function behave statistically like the eigenvalues of certain large random matrices. Physicists Freeman Dyson and Hugh Montgomery met by chance at the Institute for Advanced Study in Princeton in 1972, and Montgomery showed Dyson the formula for the gap distribution between zeros. Dyson recognized it immediately as something from quantum chaos. This is either a deep connection between number theory and quantum physics that nobody understands yet, or an extraordinary coincidence. Most mathematicians believe it's the former. The Riemann hypothesis is, in some ways, a window between the discrete world of whole numbers and the continuous world of physics, and the possibility that prime numbers and quantum energy levels are describing the same underlying structure is the kind of idea that makes mathematicians quiet for a moment. While the Riemann hypothesis asks about the deep structure of prime numbers, the Goldbach conjecture asks a question so simple that an 11-year-old could state it and understand it, and it's been open for over 280 years. On the 7th of June, 1742, a Prussian mathematician named Christian Goldbach wrote a letter to Leonhard Euler. In it, he proposed something he'd noticed. Every even number greater than 2 seemed to be the sum of 2 primes. 4 is 2 plus 2. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 3 plus 7, or 5 plus 5. 28 is 5 plus 23. Euler wrote back. His reply was essentially, "Yes, I'm completely certain this is true. I just cannot prove it, and neither could anyone else. Not in 1742, not in 1800, not in 1900, not today. The conjecture has been checked by computer for all even numbers up to 4 times 10 to the 18th power. That's a 4 followed by 18 zeros. Every single one of them is the sum of 2 primes. As far as experimental evidence goes, it's overwhelming, and yet there is no proof. What makes this particularly maddening is how close people have gotten without getting there. In 1937, the Russian mathematician Ivan Vinogradov proved that every sufficiently large odd number is the sum of 3 primes. Sufficiently large means extremely large in this context, but it was progress. In 1973, the Chinese mathematician Chen Jingren proved that every sufficiently large even number is the sum of either 2 primes or a prime and the product of exactly 2 primes. That second option a prime plus a semi-prime, is called Chen's theorem, and it's the closest anyone has gotten to the actual conjecture. Every large enough even number is at most one step away from being a sum of two primes, but the last step, closing the distance from almost always to always, without restriction on size, has defeated every attempt. The problem lives in the murky territory where prime numbers become too unpredictable, where counting arguments break down, where everything comes close to working and then doesn't. If Goldbach's conjecture is true, it suggests a beautiful regularity in the arrangement of primes. They are, despite their apparent randomness, always close enough to each other that they can pair up to reach any even number. If it's false, if there exists some astronomically large even number with no prime pair summing to it, that would force a complete rethinking of how random primes actually are. Most mathematicians believe it's true. Proving it is another matter entirely. In the summer of 2002, a mathematician in St. Petersburg posted 3 papers to an internet preprint server. He posted them without fanfare, without press releases, without even telling most of his colleagues what he was doing. He just uploaded them and went back to whatever he was doing, which was presumably taking long walks in the woods around St. Petersburg and hunting for mushrooms. His name was Grigory Perelman, and he had just solved one of the most famous open problems in topology, the study of shapes, a problem that had been open for 98 years, the Poincaré conjecture. Henri Poincaré was a French mathematician of enormous range and power, working at the turn of the 20th century. In 1904, he asked a question about three-dimensional space. If you have a three-dimensional space that is finite, has no edges, and every loop drawn in that space can be continuously shrunk down to a point without tearing or cutting, must that space be equivalent to a three-dimensional sphere? To understand why this is a question worth asking, think about the surface of a regular sphere, like the surface of the Earth. If you put a rubber band anywhere on a sphere's surface and start slowly sliding it around, you can always shrink it down to a single point. The surface is simply connected. Now, think about the surface of a donut, a torus. If you put a rubber band going around the hole of the donut, you cannot shrink it to a point. The topology of the surface is fundamentally different. Poincaré was asking about the higher dimensional version of this idea. In 3 dimensions, if every possible loop can shrink to a point, does the space have to be shaped like a three-sphere? It seems obvious that the answer should be yes. How could it not be? But proving it turned out to be one of the hardest things in mathematics. Stephen Smale proved it for dimensions 5 and above in 1961, earning the Fields Medal. Michael Friedman proved it for dimension 4 in 1982, also earning the Fields Medal. The three-dimensional case remained completely resistant. In the 1980s, Richard Hamilton, a mathematician at Columbia, proposed a strategy: use something called Ricci flow. The idea is to take any weird, lumpy, three-dimensional shape and let it evolve according to equations that smooth out curvature over time. If you start with a three-sphere and let it flow, it stays a sphere. Hamilton hoped that starting with any simply connected three-dimensional space and letting it flow would eventually deform it into a sphere, which would prove the conjecture. The problem was singularities. As the shape evolved, it would sometimes develop pinch points or tubes that blew up, where the curvature became infinite. Hamilton couldn't control what happened at those singularities. The program stalled in the mid-1990s. Perelman had been a postdoctoral researcher in the United States, where he met Hamilton and learned about Ricci flow. He turned down faculty positions at Stanford and Princeton and returned to Russia in 1995, taking a position at the Steklov Institute in St. Petersburg. Then he went quiet. For 7 years, he worked alone. Almost nobody knew what he was doing. What he was doing was solving the singularity problem. He developed new tools to classify what kinds of singularities could appear during Ricci flow, and he showed how to surgically remove them and keep going, a process he called Ricci flow with surgery. He showed that no matter what singularities appeared, they were always tame enough to be dealt with. And then he showed that if you followed the whole process to its conclusion, the shape would always end up as a sphere. The Poincaré conjecture was true. He also proved something much bigger at the same time: Thurston's geometrization conjecture, which is a complete classification of all three-dimensional spaces. Poincaré was just a special case. Perelman had essentially written the entire periodic table of three-dimensional topology. The mathematical community spent 4 years going through his proofs. They were written in a compressed, demanding style that required enormous effort to unpack. 3 different groups of mathematicians each wrote hundreds of pages filling in the details. By 2006, the consensus was clear. The proof was correct. The journal Science named it the scientific breakthrough of the year for 2006. The Fields Medal, the highest honor in mathematics, was awarded to Perelman in 2006. He refused to collect it. The Clay Mathematics Institute offered him the $1 Million Millennium Prize in 2010. He refused that too, saying that Richard Hamilton's contribution to the problem had been equal to his own, and the prize structure didn't reflect that properly. As of the last available reporting, Perelman lives with his mother in St. Petersburg and has largely withdrawn from mathematics. He has given no indication of what he plans to do next. He solved one of the greatest problems in geometry and then walked away from all the recognition that came with it, which is either a profound act of integrity or the behavior of someone who found the whole machinery of academic reward utterly beside the point, or both. The conjecture being solved didn't just answer a question about three-dimensional spheres. It completed our understanding of what three-dimensional space can look like. Every possible finite three-dimensional space without a boundary can now be categorized, understood, described. The cosmic topology community, people who think about whether the universe itself might be finite and, if so, what shape it has, took immediate interest. Perelman's work doesn't tell us the shape of the universe, but it tells us what shapes are possible. If you've been counting, one of the 7 Millennium Prize problems has been solved. 6 remain, and of those 6, there is one that sits at a strange intersection of pure mathematics and the most practical questions imaginable about computation, cryptography, and the limits of what can be known. The question is this: if you can check a solution to a problem quickly, Does that mean you can find a solution just as quickly? That might sound obvious, but it is one of the deepest open questions in all of mathematics and computer science. Mathematicians call it the problem of polynomial time versus non-deterministic polynomial time, and it might be the most consequential open problem alive. The problem was first formally stated in 1971 by Stephen Cook, a computer scientist at the University of Toronto, in a paper about computational complexity. Independently and around the same time, Leonid Levin in the Soviet Union was thinking about essentially the same question. To understand what the question is, you need two categories of problem. The first, which researchers call the tractable class, contains problems that a computer can solve efficiently. Efficiently, in this context, has a specific meaning. The time it takes to solve the problem grows as a polynomial function of the input size. If you double the size of the problem, the computation time might double or quadruple or grow by some fixed power, but it doesn't explode. Sorting a list of numbers sits in this category. Multiplying two numbers, finding the shortest path through a network. The second category, which researchers call the checkable class, contains problems where a proposed solution can be verified quickly, even if finding that solution in the first place is hard. Sudoku is a good example. Checking whether a completed Sudoku is correct takes almost no time. You just look at each row, column, and box. But finding the solution from scratch might take you ages if the puzzle is hard. Similarly, if someone gives you two large prime numbers, verifying that their product is a given number is easy. But factoring that large number back into its prime components is very hard. That factoring problem sits in the checkable class. The tractable class is clearly a subset of the checkable class. If you can solve something efficiently, you can certainly verify solutions efficiently. The question is whether they're the same set. Is every problem where solutions can be checked quickly also a problem where solutions can be found quickly? The most widely believed answer is no. In poll after poll of the research community, the consensus runs between 85 and 99% that the two classes are separate. Almost everyone believes there are problems in the checkable class that genuinely cannot be solved efficiently, only verified. But nobody has proven it. If the two classes turned out to be equal, the consequences would be extraordinary. Almost every encryption system in use today is built on the assumption that certain problems, like factoring large numbers or solving discrete logarithm problems, are genuinely hard to solve. That assumption is why your bank communications are secure, why private keys stay private, why the internet can have anything resembling privacy. If the two classes are equal, those problems become efficiently solvable, and that security essentially evaporates. But the positive implications would be equally enormous. Drug discovery involves searching through astronomical numbers of possible molecular configurations to find ones with specific properties. The search is currently done through approximation and heuristics. If fast checking implies fast solving, those searches become tractable. Protein folding, which is the problem of predicting what shape a protein will take based on its sequence, and which has applications to everything from cancer treatment to antibiotic design, becomes solvable efficiently. Climate modeling, logistics optimization, scheduling problems, anything that currently requires massive compromise between accuracy and computational cost would become dramatically more powerful. There's a way to describe the two classes being equal that sounds almost philosophical. It would mean that creativity has no advantage over verification. If you can recognize a good answer, you can find a good answer. The gap between understanding and discovery would close. Whether that sounds utopian or terrifying probably depends on what you value. The reason the problem is so hard to resolve is deep. To prove the classes are genuinely separate, you'd need to show that some specific problem in the checkable class has no efficient algorithm whatsoever. And doing that requires proving a negative about all possible algorithms, including ones that haven't been invented yet. The mathematical techniques for doing this at the required level of generality don't currently exist. In 1993, researchers showed that a whole family of proof techniques called relativizing proofs can't work because there exist artificial mathematical settings where the classes are equal and others where they aren't, and any proof that works in all settings equally can't distinguish between them. A different set of techniques, called natural proofs, was shown in 1994 to be limited by similar barriers. Every time someone tries to attack the problem, they run into a structural wall that shows why their approach can't work. The strange thing is that this very difficulty, the fact that we can't prove hardness of computation, is itself deeply connected to questions in pure mathematics, including the Riemann hypothesis. There are problems in cryptography that would be provably secure if the Riemann hypothesis is true. The two questions, one about the zeros of a complex function and one about the structure of computation, end up whispering to each other across the landscape of mathematics. There is another millennium problem that sounds, at first, like something engineers should have solved decades ago. We use the relevant equations every day. They describe how airplanes fly, how blood moves through your heart, how weather systems form, how ocean currents run, how the exhaust from your car engine disperses. They are among the most useful equations in applied science. We don't know, in a mathematically rigorous sense, whether the solutions to these equations are well behaved. The equations are the Navier-Stokes equations. Claude Louis Navier and George Gabriel Stokes, working separately in the first half of the 19th century, wrote down equations describing the motion of viscous fluids. Newton's second law, force equals mass times acceleration applied to a tiny parcel of fluid, gives you a set of partial differential equations relating how velocity, pressure, and density change through space and time. For two-dimensional fluids, these equations are understood. Solutions exist, they're smooth, they stay smooth. For three dimensions, which is where real fluids live, the situation is genuinely unknown. The Millennium Problem asks, in three-dimensional space, given a starting velocity field for an incompressible fluid, does a smooth solution to the Navier-Stokes equations always exist for all future time? Or can the equations blow up, meaning some quantity becomes infinite in finite time, a mathematical singularity? In real physical fluids, we don't see quantities going to infinity. Fluids do turbulent things, but they don't literally become infinite. So you might expect the equations to behave well. But the Navier-Stokes equations have a nonlinear term, velocity crossed with the gradient of velocity that makes them extraordinarily sensitive to initial conditions. Small perturbations can amplify. The equations have a lot in common with the kind of chaotic dynamics that make long-term weather prediction impossible. The Millennium Prize doesn't ask you to solve the equations in general. It asks you to prove either that smooth solutions always exist, or to construct an example where they don't, where a smooth initial condition leads to a blow-up in finite time. Either answer would win the prize and would transform our understanding. In 2016, Terence Tao, who is one of the most celebrated mathematicians alive and who won the Fields Medal in 2006, published work showing that a certain modified version of the Navier-Stokes equations can blow up. His averaged equations aren't the real thing, but the paper laid out a plausible roadmap for how a blow-up might be constructed even in the true equations. The paper was widely read as suggesting that the answer to the Millennium question might be that blow-ups do happen, that the equations are fundamentally incomplete as a description of physical reality at very small scales. If the equations do blow up, that wouldn't mean airplanes stop working. Engineers would keep using the equations because they work in practice. But it would mean that our mathematical model of fluid dynamics has a gap at extreme conditions, and we would need new physics, or at least new mathematics, to describe what actually happens there. The connection to turbulence is what makes this feel urgent rather than academic. Turbulence, the chaotic, swirling, seemingly random behavior of fast-moving fluids, is one of the longest-standing unsolved problems in physics. Richard Feynman described it as one of the most important unsolved problems in classical physics. We can simulate turbulence numerically. We cannot predict it analytically. We cannot say from first principles what the turbulent flow will look like. And because turbulence is inside every engine, every respiratory system, every weather system, not understanding it has real costs. Better turbulence models would mean more fuel-efficient airplanes, better cardiovascular medicine, more accurate climate projections. Solving the Navier-Stokes existence problem might not immediately give us a turbulence theory, but it would tell us whether the equations we're using are even a complete description of reality, which is a fairly pressing thing to know. Around the time Perelman was quietly working through Poincaré in St. Petersburg, and while Wiles' proof was still fresh and being absorbed, a Japanese mathematician was constructing something that would generate controversy so intense it still hasn't been fully resolved. His name is Shinichi Mochizuki, and in August of 2012 he uploaded 4 papers to his personal website totaling roughly 500 pages. He made no announcement. He sent no email to any major mathematicians. He told no press. He simply posted the papers and waited. The papers claimed to prove the ABC conjecture. The ABC conjecture, proposed independently in 1985 by Joseph Oesterle and David Masser, is one of those statements in number theory that sounds modest but has enormous reach. It makes a claim about the relationship between 3 numbers A, B, and C, where A plus B equals C, and where A, B, and C share no common factors. The conjecture says that the product of the distinct prime factors of ABC, which is called the radical of ABC, tends to be large relative to C. More precisely, for any amount of slack you're willing to allow, there are only finitely many triples A, B, C, where C is larger than the radical raised to the power 1 plus that slack. This might sound dry, but the implications are enormous. If ABC were proved, it would immediately give new proofs of Fermat's last theorem, Roth's theorem, and a long list of other results in number theory. It would also imply new results that haven't been proved yet. It's sometimes described as a kind of master key that unlocks a dozen locks. Mochizuki's proof introduced a framework he called inter-universal Teichmüller theory. The name gives you a sense of the ambition. It's an attempt to reconstruct arithmetic from the ground up, moving numbers between different mathematical universes and tracking what happens when you do. The framework requires learning hundreds of pages of new definitions, new notation, new ways of thinking about numbers that don't connect in obvious ways to existing mathematics. The mathematical community's response was essentially bafflement. For years, some of the best number theorists in the world tried to understand the proof. They organized workshops. They flew to Kyoto to meet with Mochizuki directly. They wrote surveys. And most of them came away saying they couldn't follow it. Not that they'd found an error exactly, just that the framework was so self-contained, so different from any existing mathematics, that it was impossible to evaluate. Then, in 2018, two heavyweight mathematicians, Peter Scholze and Jakob Stix, flew to Kyoto and spent a week with Mochizuki going through the argument in detail. Scholz was already one of the most celebrated mathematicians of his generation, having won the Fields Medal in 2018. After the Kyoto visit, Scholze and Stix published a document explaining why they believed there was a specific, irreparable flaw in the proof's key step. Mochizuki disagreed. He published his own response, saying Scholz and Stix had misunderstood his framework. The mathematical community has never reached a consensus. Mochizuki's proof was eventually published in a Japanese journal in 2021, but the journal's editor at the time was one of Mochizuki's colleagues, which added to the controversy. As of today, most experts in the relevant fields believe the proof has not been verified, and Scholz's position that there is a genuine error has not been publicly refuted to the satisfaction of the wider community. What makes this situation philosophically strange is what it says about mathematics. Proofs are supposed to be checkable. That's the whole point. But Mochizuki's framework is so removed from common mathematical language that the process of checking has itself become contested. A proof that no one can read is, in a practical sense, not a proof yet. This is an unprecedented situation, and it raises questions about what verification even means in a field where most people expect certainty. If the ABC conjecture is eventually proved by anyone, the ripple effects through number theory would be enormous. The connection to Fermat, which Wiles proved through elliptic curves and modularity, would also emerge from ABC via a completely different route. Two different paths to the same destination would be, in itself, a remarkable thing about the structure of mathematics. Let's take a step back and look at what all of these problems have in common, because the pattern is more interesting than any individual story. Every single one of these problems, from Fermat to Riemann to Poincaré to Navier-Stokes, looks simpler than it is. They can all be stated in a few sentences. Most of them can be understood by a motivated high schooler, and every single one of them required either entirely new mathematics to even approach, or remains open precisely because the new mathematics needed hasn't been invented yet. This isn't a coincidence. The hardest problems don't just need more effort or more cleverness applied to existing tools. They need new tools. And new tools in mathematics tend to arrive through the discovery of unexpected connections between things that seemed unrelated. Wiles connected Fermat to elliptic curves to modular forms. Perelman connected topology to the physics of heat flow through Ricci flow. The Riemann hypothesis connects prime numbers to quantum mechanics in ways nobody fully understands yet. This is why mathematicians spend so much time on seemingly useless abstract structures. They're building tools for problems they haven't identified yet. Ring theory was developed by Emmy Noether and others in the early 20th century as pure algebra, with no application in mind. It turned out to be the language you need to work on Fermat's last theorem. Group theory, developed in the 19th century partly out of curiosity about symmetry, turned out to be the foundation of particle physics. The history of mathematics is full of this. Someone builds a beautiful abstract structure because it seems worth building, and decades or centuries later, it turns out to be exactly what was needed to solve something in physics or computer science or number theory. This means that when mathematicians chase things that seem completely disconnected from anything practical, they often are doing the most practically important work of all. It just takes time for the connection to become visible. Now, about twin primes. This is another problem in the Goldbach family, simple to state, absurdly hard to prove. Twin primes are pairs of prime numbers that differ by exactly 2, 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31. They keep appearing as you go further along the number line, but they get rarer. The question is whether they ever stop. The twin prime conjecture says they don't, that there are infinitely many twin prime pairs. In 2013, a lecturer at the University of New Hampshire named Yitang Zhang submitted a paper to the journal Annals of Mathematics. Zhang was not a prominent researcher. He was largely unknown outside his department and had spent years in relative obscurity. His paper proved that there are infinitely many pairs of primes that differ by at most 70 million. Not 2, but 70 million. The mathematical community was stunned, not because 70 million is close to 2, it isn't, but because Zhang had found a way to prove boundedness at all, to show that prime gaps don't grow without limit, and his technique was good enough to potentially be improved. Within months, the Polymath project, a massive collaborative mathematical effort run online, had reduced the bound from 70 million to under 600. James Maynard, working independently, got it down to 600 on his own shortly after. Further work has pushed it into the low hundreds. 2 has not been reached, but the gap is, in some sense, closing. Zhang's result was so unexpected that Andrew Granville, one of the leading analytic number theorists, said when he read the abstract he thought someone was pulling his leg. The idea that someone they'd never heard of had broken through a wall that the best people in the field hadn't touched for decades was disorienting. Zhang was 56 years old when the paper came out. He hadn't published a research paper in years. He had worked on the problem quietly, alone, without institutional support or collaboration, much like Wiles and Perelman. That's another pattern in this story. A remarkable number of the biggest breakthroughs came from people working in solitude. Wiles in his attic, Perelman in St. Petersburg, hunting mushrooms, Zhang doing preliminary work during the years he'd spent between mathematical jobs, some of which he'd spent working at Subway. The problems that resist the combined efforts of entire research communities sometimes yield to one person willing to stay with them long enough. There is one more problem worth knowing about, one that doesn't quite fit the Millennium Prize framework, but that has consequences for everything: the continuum hypothesis. Georg Cantor, working in the late 19th century, discovered something about infinity that most people find genuinely difficult to accept. Not all infinities are the same size. The infinity of whole numbers, 1, 2, 3, 4, going forever, and the infinity of points on a line segment, any single line segment, are different sizes. There are far more points on any line segment than there are whole numbers, even though both sets are infinite. Cantor called these different sizes of infinity different cardinals. The smallest infinity is the size of the whole numbers, called aleph null. The size of the continuum, meaning the size of the set of all points on a line, or equivalently the set of all real numbers, is strictly larger. Cantor called it the continuum. The continuum hypothesis asks, is the continuum the very next size of infinity after aleph null with nothing in between? Hilbert listed it as his first problem in 1900. It was proved to be independent of the standard axioms of mathematics, meaning you can neither prove it true nor prove it false using the foundations mathematicians normally use. Kurt Gödel showed in 1940 that assuming the continuum hypothesis doesn't create a contradiction. Paul Cohen showed in 1963 that assuming it's false also doesn't create a contradiction. The question is genuinely undecidable from the standard axioms. This was the first time a natural, easy-to-state mathematical question was shown to be undecidable in this sense, and it had enormous implications for the foundations of mathematics. It showed that the axiomatic system mathematicians were using was incomplete in a deep way, one where adding more standard axioms doesn't obviously help. Some mathematicians have since proposed new axioms that would settle the continuum hypothesis one way or another, but there's no consensus on which ones to accept. This connects to a broader question that mathematics is still working through. What does it mean for something to be mathematically true if it depends on what axioms you've chosen? Are there multiple equally valid mathematics, each consistent internally but with different truths? Or is there some deeper mathematical reality that our axioms are imperfectly approximating? This is no longer just a philosophical question. It has technical content, and the answers have consequences for what kinds of mathematics it's even possible to do. Given everything that's been established over the past 150 years, some directions for where this goes next are more plausible than others. The Riemann hypothesis, if it falls, will almost certainly fall to a method that connects it to something else unexpected. The direct attacks have all failed. What worked for Fermat was linking it to a different field. What worked for Poincaré was linking it to differential equations from physics. The most promising current research on the Riemann hypothesis involves connections to quantum chaos, random matrix theory, and something called the Hilbert-Polya conjecture, which suggests that the zeros of the zeta function might correspond to eigenvalues of some physical operator that hasn't been identified yet. If that operator is found, the Riemann hypothesis might follow. Several physicists and mathematicians are working in this direction, and the tools from quantum mechanics that Freeman Dyson noticed in 1972 are steadily being developed into a more coherent framework. Goth and Maynard's work in 2024 improved a bound that had stood for over 50 years in the theory of zeros off the critical line. It didn't prove the Riemann hypothesis, but it showed the critical strip is thinner than previously known, another small tightening of the structure around the hypothesis. Progress is happening, but slowly. For the question of whether fast solving equals fast checking, the most likely path to resolution runs through something called algebraic complexity theory, which studies the difficulty of computation using tools from algebraic geometry. Scott Aronson and other complexity theorists have written extensively about what a proof of the two classes being separate would need to look like, and the rough shape of such a proof is better understood now than it was 20 years ago, even if the actual proof is still missing. The rise of machine learning has added an interesting new dimension. Machine learning systems appear to solve problems efficiently that humans haven't been able to solve efficiently by traditional means, which some people think is evidence that the boundary between the two classes is more porous than it looks, and others think shows nothing about the mathematical question at all. For Goldbach and twin primes, the work of Zhang, Maynard, and the Polymath project has genuinely opened new territory. The sieve theory techniques are being refined. Nobody knows when the full conjectures will fall, but the machinery being built is clearly aimed in the right direction. For Navier-Stokes, the direction of Tao's work suggests a blow-up construction might be possible. If that happens, it would solve the millennium problem by finding a counterexample rather than a proof of existence. And the next frontier would be building new physics or mathematics to describe what actually happens at those extreme conditions, which brings mathematical physics and fluid dynamics into conversation in a new way. There is a meta question underneath all of this that might be the most important open problem of all, one that isn't on any prize list. Why do mathematical structures, built from pure logic with no reference to the physical world, describe that world so accurately? Wigner famously called this the unreasonable effectiveness of mathematics. The same zeta function that describes the distribution of prime numbers seems to appear in quantum physics. The same differential geometry that Riemann invented to describe abstract curved spaces turned out to be exactly what Einstein needed 60 years later. The same group theory, developed to understand abstract symmetry, turned out to describe the behavior of subatomic particles. This might be because mathematics is the language the universe is written in. It might be because mathematics is so vast and flexible that any sufficiently complex physical system will match some part of it. It might be a selection effect. We notice the matches and don't notice the mismatches. Nobody knows, but the question is real, and it shapes every decision mathematicians make about what is worth studying. The problems in this story span nearly 3,000 years, from the Greeks with their compasses to Perelman in the woods of St. Petersburg. They range from questions about the shape of space to questions about which computations are possible to questions about whether fluids obey their own equations. None of them have a tidy moral. None of them are simply about being clever enough or working hard enough. What they share is this: each one sits at the edge of what mathematics can currently say, and each one, when solved or even partially understood, has expanded that edge in ways nobody quite predicted. The proof of Fermat's last theorem was supposed to close a question about whole numbers. It opened a new era in number theory. The proof of Poincaré was supposed to settle a question about three-dimensional topology. It gave us a complete atlas of three-dimensional space. The Riemann hypothesis, if it falls, will almost certainly do the same thing. The proof will need to be about something else, something that, from here, nobody can fully see yet, and the method used to prove it will open doors that we haven't imagined walking through. Mathematics doesn't make predictions about the future. It discovers things that were always true, whether anyone knew it or not. The prime numbers were always distributed the way they are. The topology of three-dimensional space was always what Perelman showed it to be. Whether fast solving equals fast checking has always been settled by the structure of computation itself. We just don't know the answer yet. There is, somewhere in the mathematics being done right now, probably in a result that looks unimportant, or in a connection between two things that seems unlikely, or in a paper being written by someone working quietly alone, the beginning of the next major breakthrough. The history of this field suggests you cannot predict who it will be, or what tools they'll use, or what the question they answer will ultimately turn out to be about. The margin is always going to be too narrow to contain the proof. The proof always exists somewhere. The work is finding it.